Yeah, we might go ahead and start, folks, just because I guess we have 2 or 3 little mini introductions going on this morning, this afternoon. So thank you, everybody. Thanks very much, folks, for joining us. This is another one of our weekly seminars from TESS, our Center for Tropical Environmental and Sustainability Science. This is a little bit different from our normal forums in that this event, which was initially going to be sort of a workshop or a group event, was inspired by a talk that Bob Wasson gave in late March, I think it was. And there was a lot of interest there because we got into some of the issues around flooding and real estate development that's happening very rapidly in this area, in flood-prone areas. And then this led on to other discussions. And we felt like there would be possibly some community interest in this. And so I will, without further ado, turn it over to Professor John Knott and let John go ahead and make a proper introduction. Thanks, folks. Yeah.
Thank you, Bill. Hi, everyone. Look, it's a great pleasure to have James here, Dr. James O'Brien from Risk Frontiers. They're based in Sydney, but James is based just outside of Canberra. James is the General Manager of Data Solutions and Resilience at Risk Frontiers, where he's been for 14 years. And Risk Frontiers is really one of the premier groups in Australia dealing with risk from natural hazards and specialising in catastrophe loss modelling. So, you know, financial losses is associated with catastrophes and climate risk and resilience. James is a GIS specialist. He's got over 30 years experience in spatial analysis. He's worked in the US, the UK, Europe, Asia, and of course, Australia. I first met James when he was a principal lecturer at Kingston University, London. He and other lecturers would bring their natural hazards class out to both Sydney and Cairns every year or second year. And when they'd come up here, they'd stay for 5 days or so. And I would take them from the Daintree down to Tully Heads or so, Cardwell Way, looking at all the natural hazards throughout our area, because that was my job here at JCU. I was the lecturer in natural hazards and taught that for 25 years. So, and James has also had 16 years of experience at Penn State University in the United States, where he did his PhD. So James is interested in large-scale hazard modelling, hydrological modelling, physical and social vulnerability indices, spatial analysis, and mapping and human infrastructure exposure to hazards. So, look, James is going to talk today about using natural catastrophe loss models. This is what people do when they really want to assess the big risks associated with the impacts of things like tropical cyclone, wind, storm surge, riverine floods, to be able to work out what the potential loss is for the insurance industry in particular, but also to society in general. So James is going to talk about that today with some applications to our local area. Thank you very much, James.
Thank you, John, for that fantastic introduction. I'd like to start by acknowledging the traditional custodians on the land that we're meeting on today, pay my respect to elders past and present, and extend a welcome to any Aboriginal and Torres Strait Islander people who may be here today. Thank you very much again for the invitation to come and talk and the hospitality you've shown me. Thanks to Annabelle for all of your logistical organisation. It's absolutely fantastic. John's right, I'm going to talk about cat loss models. I'm not going to jump into it straight away. I don't have much maths. I know you were worried last time when you gave your talk that people would run away if there was any maths. I'm not going to say there's none. It's a teeny tiny bit. I'm no good at maths. So there won't be much. Don't worry about it. Don't panic. It'll all be fine. We have a lot of natural disasters in Australia. That's not news to anybody. They're very costly. And I'd say they're scattered all over the place. There's a fair few of them in Northern Australia, though, let's be honest. We've got cyclones and floods and a number of others. So there's a few things going on in this table. So I'll go through it reasonably slowly, and I'll touch on something that Bob mentioned in his talk a few months ago, which is the loss normalisation. So I've got a ranking of losses there. They're ranked by their normalised cost, which means what they would cost if they happened today, or actually with these numbers back in 2023, but that's pretty close, so we'll go with that. So the Sydney hailstorm's right at the top, closely followed by Cyclone Tracy, and then the Newcastle earthquake, Queensland floods, New South Wales floods, and so on down the list. So this normalisation, though, it's really, really important and it's really valuable. And there's a couple of reasons why we do it. Bob did a really good job of explaining this, but I thought you may as well get it from the horse's mouth because we're the ones that do the analysis. So what it is we take the catastrophe loss list, which the Insurance Council of Australia have been putting together since 1967, and it's based off insurance claims data. So of course, already there's a little bit of uncertainty creeping in because it's only insured losses, it's not all the losses, but it's still a view and it's a good data point, but it obviously goes out of date really, really quickly. The 1967 Hobart fires are in there. They cost 40 million or whatever they cost back in the day. They're not going to cost 40 million if they happen today. So we've got to make sure that we can keep this information up to date because a lot of things have changed in the meantime. So this list started in 67. From 2016 to now, actually, sorry, from 2006 to now, so for nearly 20 years, Risk Frontiers have been normalising it and bringing it up to date. This is the fourth iteration of that, which was done in 2023. So the numbers you see are all 2023 dollars. And there's a few different things that you've got to take into consideration. There's more houses than we used to have. They're bigger than they used to be. Things cost more than they used to. And there's been some changes in building standards as well. So all of those ideas have got to be incorporated in so that you can do this normalisation. We've kept the methodology of how we do that essentially the same. When I say essentially, there's had to be a couple of little tweaks, but they don't affect the overall process, which means that you can compare between different events and you can compare between different normalisations. Not a lot of good reasons for doing that, but it is possible. So here comes the maths, brace yourselves, there it is. It's not that bad. What we do is take the loss, that LI figure, and we multiply it by a dwelling adjustment factor. How many more dwellings there are in this place than there were last time. And we do that at a pretty small scale. We do it at urban centre and locality, which is just a few thousand homes, let's say. It's a relatively small area. So Cairns is a UCL. You could think of them roughly like council areas. That's a pretty simple conceptualisation of them. We have a dwelling adjustment factor. So what houses are worth now in various states and territories has changed over time. And we do that at a state or territory scale because broadly you do get these kind of inflationary values happening, or at least measured at that scale. There's that little the Z factor there, which is the dwelling size adjustment. We all now live in much bigger houses than we used to. Not entirely sure why, but we do. So that means that houses are more expensive to rebuild on a square metre basis. And there's a B adjustment there because, as you're probably all aware, after 79, in the 79, 80, 81 period, as a follow-on from Cyclone Tracy, there were changes to building standards. So older buildings fare worse under certain wind conditions than newer buildings. And we've still got some old buildings, so we've got to make those adjustments as we go. We've done this across all the perils. Obviously, the cyclone factor is only for cyclone, but we've done it for the hail, the fire, the flood, earthquake, and so on. So I thought I'd give that little bit of from the horse's mouth background, but I promised to talk about natural catastrophe loss models and their applications and how we use them. So it would be remiss of me not to explain what the things are. I nearly swore. So there's a few different elements that go into them. You can see there's another teeny bit of maths hidden in the middle there. But risk is a function of hazard, exposure, and vulnerability. It's a bit like the fire triangle. You need all of those three things, otherwise you don't have a hazard. If you've got a hazard and an exposure, but what's there isn't vulnerable, who cares? If you've got exposure and vulnerability, but no hazard, again, great, well done, good planning, let's carry on. So I've got hazard, which is bushfire, the number of times something burns or how intense the bushfire is, or flood, the water depth, cyclone, wind speed, whatever it may be, we've got some hazard data elements that we can use. That's one of the input components. We've got exposure, which is where the assets are and how much they're worth, also important. So in the case of what I'll be talking about today, we use something called a GNAF identifier, which is essentially a dot on a land parcel that has an address associated with it. There's also building footprint data, if you're familiar with that, which can also be used. And then we've got vulnerability. And for all of the different perils or hazards, the vulnerability functions are different. They're also different for different types of buildings. So the complexity increases pretty quickly. So for flood, water depth is the main driver of vulnerability, but different building structures function differently with different water depths. So a Queenslander is already a fair way off the ground. Water flowing underneath it, more of an inconvenience. If you've got a slab on ground, you've got a slightly different proposition there. Timber frames versus brick buildings have different costs associated with them for repair or for rebuild and so on. All of those pieces go in together. There's a financial piece in the middle that processes all of this data and end up with a graph like the one on the right-hand side there. And you can look at it per peril if you have an interest in a place that suffers all of these, and you can look at them all together. There's a couple of different angles that you can take to investigate that graph. You can look at a return interval of a cost, or you can look at the cost of a return interval, if that makes any sense at all. So you can got one axis of the graph and go, I've got $100 million that I can possibly spend on insurance. How far will that get me? Like what probability am I able to lose that much money? Or you can reverse it and go the other way. Like, I must cover a 1% loss. How much money do I need? They're predominantly insurance concepts, but like most things, we can repurpose them and use them for all sorts of other practical considerations. Not that insurance isn't practical, but things that affect us on the ground or in our local communities. There's two other inputs that we can use. The red arrow that you can see going in, which is future climate scenarios. We can look at what things might be like in the future under different RCPs or SSPs at different time horizons. That's pretty handy for future planning. We can also pull in historic scenarios. So what if Cyclone Tracy hit Darwin as it stands today? Or what if the 1974 Brisbane floods happen again? Or some flood of record or some fire that we recall? What if that were to happen today? So one of the really good uses of these models is that you can start to ask and answer questions about what if this happened? What if we did something different? What if we moved houses or created a bushfire buffer or changed building standards so buildings were more resistant to wind? You can incorporate those into the exposure piece or the vulnerability piece, the hazard piece. You can make these sorts of adjustments to the modelling and then see what the financial cost or benefit of that is. So you can do what if analysis, which is pretty handy. It's a little bit like SimCity or Civ or any of those computer games that some of us may have played many years ago, except in real life and with real houses and real values. Now, I in no way intend this to be an advertisement, so this slide's not trying to advertise our capability or anything like that. It's just showing that there's these different pieces that sit inside the model, inside the puzzle, basically. And they're almost a reminder to me that we can do different things and we can ask different questions. So I've got a bunch of models for all the different perils. That's great. We can look at all of these different natural disasters that befall Australia. We can do it in individual risk mode. So we could evaluate each one of your individual houses where you live and determine a number, which is the average annual damage. What value of damage for each peril is likely to be done to your house in an average year? Or we can do it on a regional scale. We could do it for LGAs or far north Queensland or the whole country. We can scale these things up and start to make decisions about, if I were a funding agency or a council, I've got $100 million to spend. What SA1 or what suburb or what postcode should I spend that in to get the most bang for my buck? The models handle demand surge, which if there were a big disaster in Cairns, tradies and building supplies would be really hard to get access to. Everything would be more expensive. Everything would take longer to get done. So people would be in alternative accommodation for longer. Rebuild costs would be higher. Those sorts of things are incorporated in the model in the location where they happen. There's kind of a scale factor. If all of North Queensland was damaged by a cyclone, again, those effects would be compounded. You can get very precise in how you define the buildings. So are they old or new? How big are they? What are they built of? What sort of roof type do they have? Those sorts of things can be incorporated. Also what they're worth. That goes into the financial module. And I mentioned the future climate part already. So there's a lot of little levers you can pull or knobs you can twist to play around with these, to ask questions in different ways or get different answers in different ways. So there's a couple of different considerations or a couple of different ways you can imagine that you can use these models. So I've got a few examples here just to kind of stimulate your imagination and keep us going through. Not a lengthy talk, but there's a bunch of stuff in here. So just if you've got some ideas about how this might be useful, then you'll be able to attach to that and it'll be more interesting. So we calculate the losses at the highest possible resolution. Usually that's address, and that's really important for specific hazards like flood, where the flood risk changes very quickly over the terrain, and bushfire, where generally the further you are from bushland, the lower your risk becomes, and it tapers off very, very quickly. And we can, as I mentioned, do that regional breakdown of losses. So we can start to target mitigation or management or changes in what we're doing, resilience for want of a better term. Thinking more broadly, we can use historical event sets, like I said, to do exposure analysis of past events. We can look into the future. We can do that in a number of different ways as well. We can examine bushfire liability. If you're down in the southern states and you run an electricity provider, you might be worried if one of your assets accidentally starts a fire, you could be on the hook for $1 million or $100 million or $1 billion, who knows. But you can do that sort of site-specific analysis out of these models. And you can also do, and this is, I think, the most interesting thing for me at least, real-time loss forecasting. So one of the jobs we do is for an Australian government department, we do real-time cyclone, storm surge and riverine flood modelling. So when there's a cyclone off the coast like Jasper was, or Alfred or any of those, we take a bureau forecast and take them every 6 hours. We put some uncertainty around the track because of course they don't always go where we expect them to go. We model those forecasts and we produce a range of potential losses for that event. That gets done in an hour, shipped off to the relevant ministers to decide what they need to do. And then when there's another forecast, 3 hours later or 6 hours later, we do it again. So you see these evolve over time. There's a fair bit of uncertainty in them when they're a long way off the coast. By the time they get close to the coast, we're pretty much bang on. So that's a quick introduction of catastrophe models in general. I'll talk about the flood model that we have specifically, and then go into some applications of how that works and the sorts of questions we can ask. So the flood model works in exactly the same way as the previous ones. I've just changed the diagram up to make it a bit more interesting. We've got the flood risk at the top, and that's made up of a hazard component and the vulnerability component. And the exposure is kind of incorporated in there as well. I'm going to read this one because it's easy for me to see. We've got a probability of a flood occurring. You guys have probably heard, you know, the 1% flood or the 1 in 100-year flood or whatever it might be. I really don't like the 1 in 100-year flood thing, but that's a whole other ball of wax. We have the characteristics of that flood, how deep the water is, for example, or how fast flowing it is, or a combination of the two. We also have our flood vulnerabilities, stage damage curves, you might have heard, or depth damage functions, vulnerabilities in there as well. And we have direct damages, so the financial cost of the water hitting a home and destroying the home, and indirect damages, which are loss of productivity, loss of amenity in the natural environment, mental health or other health impacts. There's a number of other much more complicated things to calculate, which are normally done by actuaries who are much, much better at maths than I am. You bring those two together, not necessarily in a GIS-based risk model, but in some way you bring them together and then you get a financial loss. The diagram that's on the right-hand side is a version of what Bob showed, where as your probability of an event decreases, so as it becomes less likely, the cost of that event occurring dramatically increases. You called it power law, was it? Is that? Yeah. So there's a couple of reasons for that. One, the water's getting deeper generally as you go from a 5% flood to a 2% flood to a 1% flood. It's also covering a wider area, so you're capturing more and doing more damage at the same time. So it makes sense that it does grow as rapidly as it does. I'll talk about our flood model now specifically, because there's a couple of things that are really important and they can be easily misunderstood. So I want to make sure that I do a good job of explaining it well, because it's nuance that's easily confused. We don't do our own flood modelling, not because we don't want to, but as I'm sure John will agree, it's really bloody hard and it's really easy to get wrong. And what we don't want to have is a we said, they said situation where someone calls their insurance company and they get a different view of the risk from what their local council might tell them. So the approach that we take is to collect and collate council flood studies. They're the ones that you can see when you check online. They're the ones that are used for disaster mitigation and planning, land use planning in particular. And they are the ones that have had time and effort and money spent on them. They're verified and validated by council and panels of experts. They can be relied upon. So we accumulate those flood studies from those authoritative sources. Councils are probably the primary source, QRA is another, catchment management authorities in Victoria and some other states that have the authority to do that. The flood studies are really expensive. They're really time consuming. They're hard to do. They're not done everywhere, but just because they're not done doesn't mean there is no risk. So in some places, there is a flood risk. We know there is because we've got past event history, but it's not modelled. So to capture that, we've built something we call a flood exclusion zone, which is essentially mapping what a floodplain is in a place and then taking the opposite of it. Because what we're looking for is being off the floodplain. Because knowing you don't have a risk is just as worthwhile as knowing you do have a risk. If we can say, nothing to see here, nothing to worry about, That's really good news. Obviously, we've still got whoever may be on that floodplain that we've modelled that we can't tell you a great deal about, but it's still useful to have. The second point that's really important to grasp is we build an event set out of these flood models, and we build a 50,000-year event set. We don't try and look 50,000 years into the future. That would be heroic, foolish, idiotic, erroneous, choose your term. It's a bad idea. What we do is build a statistical distribution of 50,000 versions of what next year could look like based on what we know about the climate. So that's a really important distinction. We get a really wide view of what's possible. You get an average from that distribution if you think about kind of a normal distribution, and you can sample from it and you can pull out what the 1% might be, or the 2% or the 5%. All the rest of that's not especially relevant, except probably for the catchment correlation piece, where a 1% flood in the Barron is not a 1% flood to the north or south of here. They will have different recurrence intervals, but they may all flood at the same time, so it's worth capturing that. We validated this against a whole bunch of other data, which is great, but I will carry on so that we can get to some questions quickly. We use the authoritative flood data. We drill through it with those GNAF points, basically a dot on your house, through as many flood return intervals as we get, and we build a series of depth profiles. Places where we don't have data, we use that flood exclusion zone methodology, and we pull all of that into flood odds. So I can't read the numbers from down here, but it's roughly 7% that we know nothing about for flood for Australia, which is not too bad. There's about 40% where we know there is no flood risk, and the remainder we've got some flood studies for. It doesn't look very good when you map it, I'll be honest. I mean, it looks pretty good in Queensland. QRA's done amazing work, but there's a lot of all the states, frankly. I'm from WA, but there's a lot of WA that's just empty. Why do a flood study? There's nothing there. We don't care. Lots of Australia's like that, frankly. So there's no reason to do flood studies. So when you map it, it's not especially interesting. So you kind of need those address or population statistics to make it a bit more worthwhile. So the flood exclusion zone description is probably a bit vague unless you see a picture. I'm more of a visual thinker. I like seeing the pictures. So the blue stuff on that left-hand map, that's where the floodplains are. Again, there's not many people out there, so fair enough that it hasn't been mapped in a more detailed way. The map on the right-hand side is our validation of how this thing works. In that map, the white are the floodplains, the modelled ones that we've modelled, and the red are the, for want of a better term, professionally modelled by hydrologists or councils or local governments. You can't see it at that scale, but there's a pretty good agreement. You go to the map in the middle. In the black, we're saying no flood risk, nothing to worry about, nothing to see here. You'll be on the probable maximum flood. If you're in the white bit, there's some flood risk. If you're in the blue bit, that's where a flood has been modelled. Probably to a 1% or a 2% or 0.2% or something like that, but not all the way to the probable maximum flood. So there's still some unknown. So that's a bit of a visual representation of where we know there's no risk, where we know there's some risk, and the bit in the middle where we're kind of like, we know there's a risk, but we can't tell you how much it is. But there's something in there. So if you're in there, then that is an argument for a better flood study, a newer flood study, a flood study, perhaps if there's a lot of people that fall in the white area that aren't, that don't have a risk that's quantified. So that's the hazard piece dealt with. We'll go through the building vulnerability part reasonably quickly so we can get to the more interesting stuff that's a little bit further on. We've got to consider different building uses, residential, commercial, industrial. They're all different, they're all built differently, they all cost different amounts to fix, and they have different elements inside them that function in different ways and need to be considered in different ways. The construction type's important, whether that's timber frame or brick or steel, what's on the inside, what's on the outside, down to individual elements as well. So is it tiled floor, timber floor, carpeting, all of those elements come into it. And predominantly, the most important driver, as I said, is water depth, so how high is the floor? That's really useful information to have. There's a bunch of data sets that can help with this. None of them actually get the job done in their entirety. But we can kind of bring them all together and make them all work. So there's a number of different ways of collating that data, but there's also different ways of working out the vulnerability function. There's some from Geoscience Australia. We gather our own from event surveys. So we will go out and after a natural disaster, check the water depth through houses, talk to insurance companies, talk to insurance assessors, talk to quantity surveyors, and get values of what that damage is likely to be. It's not very fun work, but it's important. It's got to be done. The boss used to say we go to the best places at the worst times. So unfortunately true. We also have claims data. Claims data is, if any of you have ever made an insurance claim, it's not an especially fun process, but the claims data are somewhat unreliable because every insurer collects their data in different ways. Different fittings and fixtures in different homes cost money. That's often not with different amounts of money, of course, not recorded. So there are challenges to that. Anyway, what you end up with is different building vulnerability curves related to different levels of depth based on different types of buildings. Obviously, I can't share our ones from work. They're slightly privileged, but we've got some examples here, so you've got an idea of how that might work. The graph that's on the right shows something that's a bit more nuanced and a little bit interesting. These curves have little steps in them. So when you go home and you have a look at your house, you might have skirting boards that have got power points in them. So that's maybe the first 10 centimetres of damage in your house. If that gets wet, all that's got to come out. If you go up about 400 or 500 mil, that's probably where your first gyprock sheet is. So if the water goes above that, you're into the second one, or on top of your kitchen cabinets, and so on and so on. So you get these steps in the curve where as you step up, there's a vertical increase in the cost of, oh, bugger, now I've got to do 2 sheets of gyprock, or oh, now I'm into the second floor and the carpeting and the joists and the insulation, and blah, 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 blah. So these things never actually get to 1. They never get to 100%. A house is very rarely written off in a flood, unless it's swept off its piers, and that's quite rare. The houses are normally rebuildable. It'll be really expensive, let's be honest, if the water goes all the way over the roof, but it's not going to be a total write-off, which is probably good news. So for a case study, I'll say relatively close to home, closer to your home than mine. We went down to Townsville after the 2019 floods and did some work down there. I'll show that shortly, but you can do this sort of analysis, as I said, down to address level. So these aren't the actual values for these homes. To make them comparable, we picked a baseline value. We said every house is worth $500,000. That means we can compare apples with apples and we can see what the relative risk is. You could do it with raw numbers, but then you're not really saying, well, the $1 million house probably should have a higher loss than the $300,000 house because it's worth more, it's more expensive to replace. So the analysis we've done here is basically just showing with a bunch of different building types, with a Queenslander and with a slab on ground, with a 2-story and with an elevated home. With the same values, you get different average annual losses, financial losses. So that's partly due here to construction type, it's partly due to elevation. There's a little bit of a ridge on the edge of the river here. As we come southwards from the river, or down rather from the river. So those homes are a little bit higher, and then there's a gully behind them. I could say all sorts of things about why these homes are there. They shouldn't be there. They're well inside the 1%. Townsville used to have a 1 in 50 or a 2% planning threshold, which is why these homes are affected. But they're there now, so we've got to deal with them. So we can do this sort of analysis and identify particular homes that maybe the ones with the really high values, let's say the one at the very top, it's a $500 average annual damage. Well, their insurance is going to be quite expensive, I would suggest. So maybe there's some mitigating actions that they could take. Maybe we need to raise the home or something like that. Here's another Townsville example. We took some data they published online for their dam release when they were forecasting the flood back in 2019. We drilled through that with all of the losses. We used that to set up our damage surveys, and then we modelled what the expected loss would be. And at the end of February 2019, we said, we reckon 1.2 billion. Like, we'll stand by that number, and that's our number. And then when everything, I nearly said washed up, when everything was said and done, when all the calculations had been done, roughly a year later, it shows up in the ICA data list at around about the same price. Now, one data point doesn't mean that we're right all the time, fully admit to that, but it does give an indication of these models are pretty good and they'll get you pretty close. And if they're broadly consistent in predicting damage and loss and costs, especially over a large area or over a large set, then maybe there's something we can do with this. So enough about the contemporary stuff for a minute. Let's see how we could run this into the future. So what's Cairns going to look like in 2045? I don't know. I'll be significantly older than I am now. I probably won't see it. But we can do the calculations. We can take the Queensland government's population projection numbers, which are up there, how much they anticipate the growth will be. We can do something similar with dwelling values. If on average they go up at 4% a year, we could do that. There's some government data that suggests what property values may be at that time as well. We now have something of a challenge though about where do we put them, which gets to planning policy and the location of our exposure. It's all well and good to say, all right, they're going to be more expensive and there's going to be more of them, but where do we put them? We need to work out what our choices are there. And this is a place where these models can help. I'll show you a different example shortly, which will probably give you some ideas about how we can do that. Do the same thing with climate change. We can do this two ways. We can do it with everything as it sits now and just see what it's going to be like in the future. Or we can do it with those changes incorporated. All right, let's put another 50,000 houses in the Cairns LGA and work out what the losses or costs are going to be of that. So the way that you do this with climate change, and it works across all of the models, but flood's a good example. You pick your climate change scenario, whichever one you feel is credible, RCP, SSP, whichever it may be. You pick the time horizons that you're interested in. Frankly, 2030 is pointless. We're basically there already. We don't see much change beyond 2050 because they're all essentially the same at that point. You can pretty much pick 2070, 2090, 2050 and so on. You change the inputs for the models, so you adjust the climate variables. If we're going to have more rain or less rain, if it's going to be drier, have stronger forest fire danger index, for example, you can adjust all of those input variables and you can get some, I wouldn't even call them rules of thumb. You can get some increases or decreases in certain places. You can apply those to the model and then you can essentially recreate your event set and see what Cairns may look like in 2030 or 2050. It's really good fun. What does it look like? So this is Cairns, present day, with Geoscience Australia's nexus values distributed across the population. So I don't know what everyone's individual house is worth. I don't want to know or need to know, but we can make assumptions about that from higher level data that's at a lower resolution, and we can scatter that across an area and assign values to certain houses. So we know what the houses are worth. We know where they are in the environment. We know what the flood depths will be at each of those houses for different return intervals. And we know what the vulnerability is of what it costs when the water gets to a certain level. So we can model it and then we can map it and we can show that with the data that we have, and I know Cairns City Council is doing some new flood modelling, so this may change at some point, and there'll be new data and new flood studies. We can work out that those red areas are the ones that have the highest average annual loss, and the ones that are the kind of the dark purple colour have the lowest average annual loss. So maybe there's more at risk in those locations. Maybe there's higher values in those locations. Either way, the red doesn't look very good. Not just as a colour choice, but those places, there's something going on there. So that allows you to target action in those particular places. I've highlighted a couple of numbers up there, but first I'll talk about the yellow circling. What's interesting is that there are houses, and you can see it on that chart there, there's $104 million of loss in the 1 in 20 or in the 5% flood. That's not very good. That's probably an historic failure of planning and allowing those houses to be built where they were built. There's some in the 1 in 50, there's some in the 1 in 100. And then once you go past the 1 in 100, the losses dramatically increase. Back to Bob's kind of power law diagram and the one that I showed earlier. Of course, you've got a larger expanse and you've got more water. But the other thing you're seeing is how flood planning works, because there's a big step up in that curve once you go past the 1%. So you've got a whole bunch of properties that are essentially stranded or trapped assets or legacy risk that we wouldn't allow to be built today. And then after that, the curve flattens out a little bit. So there's a lot of damage, a lot of cost that's done in that first little bit, and then it basically tapers off. So you can identify where there's a problem area. And it's a bit of a pointer as to why we've got these kind of flood planning levels. Because those things happen an awful lot. And the more they happen, the more it costs. So keep that one in mind. I might kind of pick a number you're choosing. Actually, don't worry about picking a number. I'll show that it roughly halves. What if, and this is a massive what if we lifted every house in Cairns by a metre? What if we increased the floor height of every house in Cairns by a metre? Now, I know that's going to be really hard if you've got a slab on ground house. If you've got a Queenslander, it's slightly easier. You can just get under with some props and jack it up. But what if that were possible? What if we could notionally reduce the flood depth at every property by a metre? Well, it roughly halves the average annual loss. That's pretty good. Probably a decent return on investment if you look at the decrease from the 1% originally of $3 billion of loss down to $1 billion of loss. You had a 1% flood in Cairns and it caused $3 billion worth of damage. That's going to be a bit of a problem. If you could say, all right, we're never going to have this again. We're going to lift every house by a metre and save the next time this happens, and it won't be in 100 years' time, of course. The next time this happens will only notionally cost us $1 and a bit billion. That's a pretty good return on investment. Because we all understand the 1% flood doesn't happen once in 100 years, right? We're all across that, I'm sure. Yes, excellent. Really? Right, yeah. So, not at all. It's a very good distinction. Every now and then you'll hear on the news in certain places, someone will be interviewed and they'll say, I've been told it's a 1% flood. It can't possibly be a 1% flood. We had one 3 years ago. So the problem with the 1% flood is, or the 1 in 100 year flood as it used to be described, people associate the duration, the 1 in 100, that's the frequency of the thing. It's got a 1% chance of happening every year. And I think the best example, particularly as Australia has a reputation for being a gambling country, is how many times has the 100 to 1 horse won the Melbourne Cup? Who else's dad used to be a bookie? Anybody know? 4 times in 160 years, let's say. That's not uniformly distributed across those 160 years. The 100 to 1 horse won it twice within 4 years at one point, which is a bit like the periodicity of 1% floods, if you think of it like that. You might get 4 in 160 years. You might get them a couple of years apart. So that's a really important consideration. Everyone here knows that now, so that's great. What if we went even more crazy and we put everything 2 metres higher than it currently is? I mean, if you're jacking up a slab on ground house 1 metre, you may as well go the whole hog and go for 2 metres, right? Not a problem. Brings the loss down by an awful lot. But what it doesn't really change are these houses that are still inside the 5%. It's gone down from 100 million to 27 million, but they're still there. I haven't dug into it closely, but my argument would be they can't stay there. They've got to be moved from a land planning and a cost perspective. Those houses are most definitely in harm's way. We're not helping anybody by allowing those people to continue to live there. Their property, their life is at risk because that loss has a 5% chance of happening in every given year. I personally wouldn't like those odds. Like that's not a good outcome. All right, jumping forward, way forward under a climate change scenario. And this is a bit odd. That number hasn't really changed. If we don't move any houses, and I'm not in any way suggesting I'm denying climate change science here, I'm just suggesting that with the data that we've got, scaling up roughly what we've got with percentage increases in rainfall, not a lot is changing on a floodplain as big as the Barron, which is probably good news, but it means we've got to keep on top of planning, I would suggest, so that we don't put anything in harm's way. All right, so to wrap up and leave a little bit of time for questions, I did tell you I wasn't going to talk for an hour, but 45 minutes is a bit rough, especially late in the day. CAT models are really good at this kind of scenario analysis. What if, choose your own adventure, let's drop some houses in a place, let's take some houses away from a place, let's raise floor levels, let's raise flood levels. Maybe we build a levee, maybe we don't. Let's see what happens. The really useful thing is you get dollar values for that. Dollar values are really good at motivating people. Everybody wants to see what their house is worth. Nobody wants to see that their insurance premium may go up. You can do a benefit cost analysis for council. It would cost us $500 million to build the levee, but we'll have X $100 million in avoided cost on an annual basis going forwards. Levee might be a bad example. I knew I'd get a bite. If we put these houses here, we will get this much in rates, but it will cost the ratepayers this much in insurance. if we don't build this road, or if we build this road higher, it will cost this much, but save this much in the future. You can do this analysis at any scale, which is really, really handy, right down to individual address level. So you can use it for risk selection, targeted mitigation. You can scale it up to regions, so you can do multi-scale analysis. And it's important I leave you with the message that all models are wrong. Some models are useful. Don't forget that. They're always wrong. Not always wrong, but they're useful. So, have I got any questions?
Yeah, go on, John. So they can hear you online.
Thanks, James. That was really, really good. I think that's very useful information for a lot of people here. You mentioned that with climate change, the scenario on the Barron floodplain won't change a lot. There's a number of people here who live on the Barron floodplain that live below the 1% flood level. Could you explain why that is? So rainfall is going to increase, flood discharges will increase, but you're saying that you said that the scenario on the Barron floodplain isn't going to change a lot. I know the answer. I want you to explain it to everyone.
So there's a number of answers. Partly it's uncertainty. Partly it's having a very big floodplain that has only limited capacity that can put through it. Feel free to correct me on any point. And so the uncertainty is the big one. We're looking a long way in the future. We are scaling broadly by, let's say the rainfall increases by 7%. At that time period, we'll increase the flood depth by 7%. We're going to have an edge effect by doing that, because 7% on 0 is still 0. So instead of the flood surface getting to the edge like that, we'll get to the edge like that, have a drop off. So whatever happens out here will be missed. So there's an uncertainty or an error that's introduced there. So that will be part of the challenge. What have I missed? Uncertainty in climate models, lack of edge effects. The Barron floodplain only captures so much. Oh, we don't have flood data for everywhere either. That's our other challenge. We've only got it in some places. There may be areas that are currently modelled which flood and increase, but there may be areas which are not currently modelled which may also flood that we don't have. What did I forget, John?
No, that's it. I guess the spatial extent doesn't vary that much, but the depth increases considerably, which therefore the velocities increase, which therefore mean there's greater risk to life and greater potential damage to properties.
Absolutely. And these models are only working currently on depth. So the velocity element, the threat to life, isn't incorporated in that. Any questions?
I guess just on that last point you made, these models are only based on depth. So are there models based looking at velocity that are in the pipeline?
I love the pipeline pun, thank you. You can, so councils, when they do their flood studies, will often produce depth surfaces. Sometimes they will also produce velocity surfaces. And then the goal, or what should be done then, is you combine the depth with the velocity to get a hazard. Because obviously the deeper the water, if it's slow moving, it's still a threat, but shallow, fast water is also a problem. So you do build essentially a model of hazard using depth and velocity. Those surfaces aren't always produced, and sometimes when they're produced, they're not made available. So it can certainly be done. The majority of the research, though, is focused on depth being the primary driver of damage to property, but there is also work that's done in emergency management, so SES and others, looking at velocity of water and what's survivable. So it's a slightly different application, but it is certainly possible, yes.
Cairns Council will be doing velocity.
Where I easily done it for 5 minutes a second outside.
All right. Now, the only thing is we do try to use the mic, because otherwise it doesn't get recorded and people online don't hear. So anyway, Rob, that was such a good talk. One question, just intuitively looking at your map of Cairns, I couldn't quite tell exactly where some of those inland, so some of those areas in red there, I guess I would have thought places like north of Cairns on the beaches, Machen's Beach, Holloway's Beach, Yorkie's Knob, some of those places, it seemed like they were just really hit, for instance, for the last large cyclone that we had here. But those inland areas are showing up as red. And I'm just, why is that? Can someone explain that? Yeah, what suburbs are those? This is going to be a hard one to ask him to do that because he's from Sydney, for Pete's sake. So, or
Yeah, which is going to be the primary driver. It's going to be a population density. We haven't normalized these, so we haven't said on a per capita basis or a per house basis, this is what the loss is. So if there's a greater number of properties in there, and even if they were the same value, if they're all $500,000 houses, if you've got 1,000 in the red area and 100 in the purple area, you're going to have a vastly different number. As for what suburbs they are, I've deliberately chosen and not labelled suburbs and localities because I didn't want to upset anybody, because you can probably work out. And I probably should have even fudged the numbers a bit more, but it's more of an exemplar. The other potential reason is the detailed Cairns City Council, Cairns Regional Council, my apologies, flood data is more to the south. The data for the north is QRA's slightly lower resolution basin modelling. So because it's done on a slightly lower resolution, it misses minor changes in elevation. So it can underpredict or overpredict the risk. I'd suggest it's potentially underpredicting the risk in these locations.
mm-hmm.
Looking at it at this scale does mask the risk as well. It would be for a detailed study of the beaches, you would go essentially address by address and colour them in the same way and be like, oh, that one's the problem. That one's driving most of the risk and all the rest of them are fine, for sake of argument.
Right. Okay. Other questions, comments? Yep. Bob.
Thanks, James. That was very informative, and this might well generate some increasing interest. To a comment and a question for quite different phenomena, not floods. The Finns are actually looking 100,000 years into the future for their deep radioactive, high-level radioactive waste disposal, but they're looking at glaciation and erosion and isostatic adjustment of land surfaces. So these are things which we understand quite well, and the glacial cycles, etc., driven by the Milankovitch phenomenon, blah, blah, blah. So looking that far into the future is possible. Well, is it possible? I'm not going to be here to test it, but certainly they're trying to do exactly that. But I take your point about the flood story. The question is this, and I may have this wrong, but it seems to me what you're doing in the analysis you've presented here is a form of stress testing.
Absolutely.
And I mean, banks do it. The American banks do it very poorly. Others do it better. And I think Australian banks do it. I don't know whether they're good or bad at it. So is that your view, that it is a form of stress testing?
Oh, it definitely is, yeah.
Yeah.
Again, it's multi-scale.
Yeah.
So, and I wouldn't suggest anybody go and license our software to run it on your house by house basis, but you could certainly do it regionally. You can intersect it with additional data that points at household resilience. So insurance affordability, for example, there is a metric once you are paying more than, let's call it, a quarter of your fortnightly income on insurance, it's deemed to be unaffordable. So you can overlay Bureau of Statistics information with this and say, okay, these areas have a median fortnightly income of X, apply some logic to these numbers and be like, well, if that's the average annual loss, the premium would be broadly this much to cover it. That is generally more than this area earns. Therefore, insurance is likely to be unaffordable in that place. How do we fix that? What do we have to get that number down to? Because you can't get the incomes up, that'd be lovely, but what do we have to get that number down to make insurance affordable again? And there has been a lot of work that's been done in that area. The Northern Australian Insurance Pool Task Force, the Australian Reinsurance Pool Corporation have done that with cyclone, for example. What do we need to do to adjust the premiums to make insurance affordable in cyclone-prone regions, for example? And you can do the same analysis with flood or any peril, frankly, but we're talking about flood.
So thank you. I'll talk to you later about that. As I said over lunch, we've compiled data for paleo floods, probable maximum flood for 6 catchments on the Queensland coast. And the largest floods are not in the gauge record. They're older. But if you could apply those to the analysis you're doing,
yeah, no question.
and you could do a stress test using this wider range of flood magnitudes.
You'd stick it in, it's way back at the start. You just stick it in as an historic event.
Yep. Okay.
Just
Thank you.
It's not gauged doesn't mean you can't, make it up, essentially.
We didn't make it up.
No, that's what I mean. We think it's this flow rate at this gauge, therefore we'll stick that in.
More from you.
I have no doubt.
Thanks very much. Very informative. I can see that you work closely with insurance, the insurance side of things, and it's yes, there's a risk. Yes, there's an event. This is what it's going to cost. So the insurer or the insurance company uses. I can see now why they ask me all those questions when I actually ring up for my house insurance. You know, what are the floors made of, etc. And I guess the implications of it come down to planning. I mean, I don't like the idea of raising the floor in our property, which in Yorkeys Knob, because we're on the ground floor of a three units, and Bill actually owns the top one. So we'd be crouching down with a floor unless we adjusted the ones above. I don't think we could lift that one. But lifting, particularly I'm thinking in areas like Holloways or Machins, if you were to bring in a couple of 100 cubic metres of soil to lift your whole block of land, that's okay for you, but it doesn't actually help the general level. It doesn't help the neighbours. It doesn't help the levels of the flood. And similarly, the planning of these things comes back to generally to council, and council is not the one that's actually incurring the loss, other than people move out and they don't get the rates income. They're not the ones that are actually copying it. So they're doing a flood study now, which will say, all right, here's the risk, which is likely to be higher than it has been in previous ones. But I just sort of don't see or quite see how that all comes together in sort of forcing council to do things like not letting people do here, or who's going to be buying out these properties that are not viable in the future, etc. It becomes a very high level political question, as it is very much so. I guess that's more of a comment, but might.
So there are definitely buyback schemes in place to buy, habitually is probably the right word, flood affected properties. They are usually significantly undersubscribed. So for sake of argument, I usually use an example if you don't mind. Let's assume your house is worth $500,000. It's flood affected last year, the year before that. You've had enough, you can't get insurance. I turn up and say, I'll give you $400,000 for your house. You'll probably tell me to go far away. Fair enough, and maybe give me some instructions of what to do when I get there. Fine, perfectly understandable. But even if you took the 400 or the 500, where do you go? You've got to go and find somewhere else that's not at risk. And we need to do that for probably all your neighbours. We can't leave you guys living on the top floor because you'll be isolated in a flood. That's a bit inconvenient. You won't like that very much. SES will have to come and rescue you. Who knows how long you'll be there. So we're going to have to take the whole thing. So you've all got to now go and find somewhere else. If it's only a few properties, maybe we can turn it into a park or something, you know, improve the amenity of the general area. What do we do if it's kind of checkerboard pattern? You guys have probably seen Detroit, for example, where homes have, you know, been vacated, people couldn't pay the bills, they've just left the home, it's burned down. You get this really weird, sparse population distribution. That creates a bigger problem for council. They've still got to maintain the roads. Electricity companies still got to maintain the supply. Water companies got to maintain the supply. Now there's bugger all people there to cover the cost. So they've pretty much got roads to nowhere. I don't know if a buyback actually works unless it's en masse, like Grantham style. And there's all sorts of things you could say about that approach and how it was undertaken, but it did move the flood risk up the hill and pretty spectacularly, pretty quickly. But it was, I would suggest almost a traumatic event was required for that to happen. I wouldn't wish that on anybody, but I don't think it happens with, I'll choose my words very carefully, but I'll still be wrong, relatively minor effects. So, you know, a metre of water through your house, that's not pleasant. Like, I know that, it's really unpleasant, but it's not catastrophic. It's not multiple metres over the roof. It's not tens of fatalities or more. I don't think that scale of event drives significant change. I don't want the horrible events to drive the change, but I don't think there's any other motivation, frankly, for people to make that change and either move out voluntarily and try and sell their house or just walk away and leave it. We've got too much money tied up in real estate. I don't think there is a political appetite or the money to buy us out of that problem. I think the best we can hope for is that we stop making those mistakes in the future. And at some point, someone else, and it's always someone else, will have to deal with that stranded asset problem of those homes. I genuinely don't have a solution for that one, but I will point out that the raising everything by a metre is essentially a thought experiment exercise. It's a cop-out, basically. Or what if we did this? You wouldn't do it for every house. You would do it much more targeted. You would pick the houses in Machin's. You would pick, you know, the ones wherever. You'd be like, that one, that's a problem. It's low. It probably shouldn't have been there. Maybe we can take it away. Maybe we can lift it. Maybe we can do something. There's other things we can do as well. We can change the interior fit out of these buildings. We can stop letting people build under their Queenslanders or their high-set homes. There are a number of other factors that are not, let's just put the thing way up in the sky. But it's much easier to do this really, really quickly for a presentation to give some numbers than it is to go through house by house and make minor adjustments to everything. It also doesn't show up because then you're like, well, what happened there? Why is this one different? Why is that? So, yeah, it's much easier just to stick them all up in the sky and be done with it.
James, we hear a lot these days about there's a housing affordability crisis in Australia or housing crisis in Australia. And I'm sure this is something you deal with frequently. Are there certain places, whether that would be states or cities or councils, where you see prevailing trends likely to be moving in the wrong direction, in which there's a lot of building happening in high-risk flood areas? Are there certain places that you could identify or are willing to identify, considering you're being videotaped right now? But yeah.
I don't live in them, it's okay. No, I think there's a different challenge, and I don't think there are areas where, well, there are areas, I'm unaware of them off the top of my head. I think there's a different problem around planning law in that if something's approved previously, historically, let's say, it doesn't update with new planning rules. So Queensland, I understand, and please correct me if I'm wrong, when you're doing flood planning, you can give consideration up to the probable maximum flood, not just the 1%. So the concept that a 1% line is somehow magically protective of flood, it no longer exists. You can consider all the possible floods that are available. I think that is a problem. I think there are areas where there's those locations in Townsville, for example, where they would have been approved under the old 2% regime. Those houses are pretty new. So a reconsideration probably should have been made there. That what we said was okay in the past, we've said a lot of things are okay in the past in a lot of different areas, a lot of different forms of, you know, society, they're not acceptable anymore. And I think land use planning can be one of those as well. And there's another consideration which you didn't ask, but I'm going to answer anyway, because I learned that off a politician once. We have this fascination with a probabilistic based risk assessment. Everything's a 1% something or a 0.5%. We're looking at a line on a map that's got a probability attached to it. We're not looking at a line on a map about a consequence. So, for example, the 1% flood in Cairns through, you know, anyone's house here might be 20 centimetres or 50 centimetres, or it might be a metre. Now that goes from being inconvenient to being bugger, you know, that's going to be expensive. In the Hawkesbury and that 1% line is 2 metres or 3 metres deep. That's not inconvenient, that's life-changing or life-ending. So why don't we have a consequence-based planning scheme? If the 1% of water through my house is a few centimetres, so what? I'll build it a little bit higher. If it's a metre, all right, well, I need to be a fair bit higher. If it's 2 or 3 metres, I shouldn't be there. Like, we should be some other place. But we're attached in our legislation and in our thinking to build outside the 1%. Like somehow the 0.98% isn't going to hurt us. Well, we know it will because we've had those big floods and the 1%. The water doesn't just stop at the line, it's not magic. So I think we need to be more intelligent and more considered in how we do our planning. Got a question behind you.
So if we looked at planning by consequence, how would that alter insurance premiums?
Well, it should lower them, right? I would make the argument that premiums should be lower because the risk is lower, the consequence is lower. So the average annual damage is lower. So that portion of the premium should be less. It's going to have some pretty weird consequences, pardon the reuse of the word though, around land use planning and allocation, because you will now have pockets, for example, in any of the beachside suburbs where the water's over a depth and you can't build there. So you'll have these little holes. Okay. The rest of the houses are fine. You can, maybe you can build in different areas that are inside a notional 1% flood, but the waters are very, very shallow. If the residents are aware and prepared to accept that risk, or whatever the depth is. If it's below 10 centimeters, all right, stuff's going to get a bit wet. You can only have tiled floors downstairs. You can make consideration around that. Your power point's got to be up in the air. But if you're accepting that it's going to get wet every now and then, and we'll just mop it out and carry on with our lives, fine. You can live there. But if it's going to be a metre through and it's going to be roughly the same frequency, then I think that's a different story.
Okay, yep.
Thank you. Yeah, I was just wondering whether the banks are actually looking at the data, because we know the insurance companies are, but are the banks saying we're not going to loan money to build in that area, and are they using the same data?
No, it's a really good point. It's not going to be a popular answer, but so the insurance companies look at that. The banks don't, and it is a bit confusing as to why they don't. Insurance is relatively straightforward. It's a one-year contract. So at the end of that year, if your insurance company no longer thinks you're an acceptable risk, they'll either not insure you or they'll increase your policy. And you will either go somewhere else or you'll pay the, whatever the markup is. That's your choice. They have the ability to step out. Your bank with a mortgage doesn't have that. On average, most people have mortgages for 5 to 7 years. So they're stuck with you or you're stuck with them, depending on your point of view. But banks don't undertake that investigation. There is a little note for anyone who's got a mortgage. If, when the statement comes in, there's often a sentence that's printed on there that nobody pays any attention to that says you must retain insurance for this mortgage to be valid. Has anybody seen that? I wonder how many people pay attention to that. At what point, when your insurance premium goes past 10,000 or 20,000 or 30,000, do people make the decision, bugger it, I'm going to keep my house. The only way to keep my house is to save $2,000 a month to pay my mortgage. I won't pay my insurance. I don't know. But I can imagine it's a decision that comes up possibly monthly for some people when they're looking at their bank statements and credit card statements and forgetting that one little sentence that they only see once or maybe twice a year on a statement. So it's late in the middle with the question. I'm not sure we're still going out.
Statement.
Oh, okay.
I think that the bank, I would assume that the bank is assuming that the council is doing their due diligence, or whichever land, planning authority, to not allow people to build on the wrong land. Therefore, that would be my take on the bank.
I'm not sure they're relying on the councils. I think they're assuming that they could have a loss at any return interval, and just because you're outside the 1% doesn't mean you're flooding or any other damage or breakage. Frankly, there's not a fire planning zone really. In certain areas you've got to have a certain barrel rating, but that doesn't protect your home. There's cyclone wind standards, but you could still lose your roof and be up for a massive amount. If you have an earthquake, same thing. I don't have to have earthquake insurance necessarily. I live outside of Canberra in a really seismically active area. I really hope my insurers aren't listening. Probably are. But no flood and no fire risk. But on my bank, I do maintain insurance. But it's not just flood that's a consideration here. There's all sorts of things that could go wrong. So. That's very true. And on the balance of probability, given there's, let's call it 4 banks, 5, 4.5, whatever, they are probably going to make the argument they've got a distributed enough portfolio that if, for sake of argument, all of NAB's mortgages on the northern beaches or in Cairns or wherever were wiped out, they've still got the rest of the country. and you still are liable to pay the thing. And possibly.
Can I just make a point, taking back to raising the houses? I live at Machan's Beach. I'm fortunate I live in Machan's Heights. So
I think that's an in-job.
after the floods, the community association asked the state member about the same sort of assistance that was given in Brisbane, the Brisbane floods, where people received grants to raise their houses. And we said, instead of building the same, can we get financial support? And the answer was no, because it was just a one-off event. We hadn't been flooded often enough to warrant it, which I think is pretty short-sighted.
I don't think I can say anything positive about that. I might not say anything at all. Nobody wants. It's an interesting point of view.
Further questions?
I suppose there's a follow-up question for the minister. How many is enough? Like well, I'm cheeky, so I probably would ask that question. But